All right, today we're going to dive into one of the most elegant, most powerful tools in all of physics and engineering, Gauss's law. So if you've ever found yourself wrestling with some absolutely gnarly integrals just to find an electric field, trust me, this explainer is for you. Let's kick things off by looking at the exact problem we're trying to solve.
So, does this look familiar? Yeah, I thought so. If you've ever tried to calculate the electric field for something as basic as a charged wire using Coulomb's law, you know the pain. You end up staring right down the barrel of an integral that's, let's be honest, complicated, super time-consuming, and just a bit of a nightmare to solve by hand.
And that really is the heart of the problem, isn't it? The second you move from one little point charge to, say, a line of charge, or a sheet, or a sphere, well, Coulomb's law makes you sum up an infinite number of tiny little pieces. I mean, it's powerful for sure, but wow, it is often brutal.
But what if I told you that for certain very, very common problems, you could just bypass all of that complicated math and get straight to the answer with some simple algebra? Well, there is a way, and it just so happens to be one of the four cornerstones of electromagnetism. This right here, this is Gauss's law. Now I know, it sounds a little abstract. Electric flux, closed surface, what does that even mean in the real world? Don't worry about it. We are about to make this incredibly intuitive. The key is to just forget the formal math for a second and really think about it visually.
So to really get a gut feeling for what Gauss's law is all about, let's use a really simple analogy. I want you to imagine you have a sprinkler head, and it's sitting inside a big, transparent, totally sealed box.
Now the sprinkler itself, the source of all the water, that represents the electric charge that we've trapped inside our box. We'll call this Q enclosed. It's the source of the stuff that's about to flow outwards.
Okay, so you turn the sprinkler on, and water shoots out in every direction. The total amount of water that's flowing through the walls of that box every second, well, that's the flux. In our world, it's the electric flux. It's just a measure of how much electric field is piercing through our imaginary surface.
Now here is the core, beautiful idea. Does the shape of the box matter? Nope. What if there's another sprinkler sitting outside the box? Still nope. The total amount of water flowing out of the box only depends on how strong the sprinkler inside the box is. That is the genius of Gauss's law.
So, when you boil it all down, it comes to this beautifully simple relationship. The total flux coming out of your imaginary surface is just equal to the total charge you've trapped inside it. Total flow out equals the total source within. That's it.
And this is how physicists write down that sprinkler analogy. This equation is the integral form of Gauss's law. See that little circle on the integral sign? It just means we're adding up all the flux over a completely closed surface, our sealed box. The left side is the total flow coming out, and the right side is the source that's stuck inside. It's the same simple idea, just written in the language of calculus.
Okay, so how do we actually turn this beautiful concept into a problem-solving machine? Well, the entire trick, the whole game, is choosing the right imaginary box. And it has a proper name, the Gaussian surface.
And the key to choosing the right surface, the secret ingredient, is one word: symmetry. If your charge is spread out in a really regular symmetric way, you can choose a Gaussian surface that makes that scary-looking integral on the left side of the equation just become trivial.
And the rule is so simple. You match the shape of your Gaussian surface to the symmetry of the charge. You got a single point charge, which radiates its field out equally in all directions. You use a sphere. Got a long line of charge? You use a cylinder. And for a big flat sheet of charge, you use a rectangular box, which is sometimes called a pillbox. This is how we set ourselves up for an easy win.
So here's the game plan. Every single time, it's a four-step process. First, you look at the charge and you identify its symmetry. Second, you pick the matching Gaussian surface from our list. Third, you just write down Gauss's law. And fourth, and this is the cool part, because of the symmetry, the math basically collapses, and you can solve for the electric flux density, which we call D, which is basic algebra. You can think of D as that flow per unit area we were talking about earlier.
So let's see this thing in action. Let's take an infinitely long line of charge. Remember that nasty integral from the beginning? That's the hard way. Now look at the right. That's the Gauss's law approach. There's no integral in sight, just a nice simple algebraic result. So let's walk through it step by step.
Okay, so steps 1 and 2. We have a line of charge, which, you guessed it, has cylindrical symmetry. So we choose a cylindrical Gaussian surface. We'll give it some length L and a radius ρ, and we'll center it right on the line. Now the electric field is going to point straight out from the line, perfectly piercing the wall of our cylinder.
And now for the magic. Steps 3 and 4. First, let's look at the right side of the equation, Q enclosed. Well, that's just the charge per unit length, rho L, multiplied by the length of our cylinder, L. Easy. Now for the left side. Because we were so clever and chose a surface where the d field is constant and points straight out, that whole scary integral just simplifies to d times the surface area of the cylinder wall, which is 2 pi rho times L. And look at that. The length L is on both sides, so they cancel out. Now, one simple division gives us the answer for d. No crazy integrals, just simple, clean algebra.
Now, I know this seems almost too good to be true, so we absolutely have to talk about the all-important gotchas. Gauss's law is an incredible shortcut, but you have to remember it is not a magic wand that solves every single problem.
Take a look. On the left, we've got a perfectly symmetric point charge. We can easily draw a sphere around it where the d field is constant everywhere. Simple. But on the right, we've got just a random blob of charges. Where would you even draw a surface where d is constant? You can't. The symmetry is gone, and so is our shortcut.
And the source material is very, very clear on this point. It is so crucial to understand this. Gauss's law is always true. The total flux out of any surface always equals the charge inside. But, and this is a big but, it's only useful for calculating the electric field when you have the symmetry to pull that d term out of the integral. If there's no symmetry, you're right back to the hard way with Coulomb's law. Okay, let's wrap this up with the key takeaways. Number 1, the core concept. Just think, sprinkler in a box. The total flow out of a closed surface is decided entirely by the source that you've trapped inside of it.
Number 2, remember its big limitation. Gauss's law is your absolute best friend for problems with perfect spherical, cylindrical, or planar symmetry. For pretty much anything else, it's a beautiful truth, but it's not a useful calculator.
And number 3, the practical takeaway. Identify the symmetry. Then, pick your weapon. A sphere for a point, a cylinder for a line, and a box for a sheet. That's the key to making the math fall apart in the best possible way.
And just to leave you with a final thought, Gauss's law isn't just some neat trick. It's the very first of the 4 legendary Maxwell's equations that govern everything about electricity, magnetism, and light. It reveals this deep, beautiful symmetry in our universe. And it kind of makes you wonder, right? What other elegant shortcuts are out there just waiting for us to understand?